So last time we've been talking about matrix operations, and we had defined a few things. We defined matrix addition, subtraction, and then scalar multiplication, right? So say that we asked you to do this matrix addition problem. What would we get as our answer here? What would the first entry here be? 5. Okay, and then the next one, the one right here, would be 1. And then the one right here would be 5. And the one right here would be -3. So again, how did we do that? We just added the corresponding entries together, right? 3 plus 2 gave us 5. Okay? That should have been pretty easy. What if we had this subtraction problem? Yeah, this is undefined. We can't do this. Why? What's the problem here? Yeah, the dimension for this one is 2 by 2. What's the dimension for this one? 2 by 3. And we know that if the dimensions aren't equal, we can't do addition or subtraction, right? Everybody's okay with that? So the dimensions here, what does this number 2 represent? It's the number of rows, and the 3 then is the number of columns. Everything we do matrix-wise is always going to be kind of written like that. We're going to do rows first and columns second. So for scalar multiplication, we could ask you to do something like this. Remember, a scalar is just like a regular number, like the 3 out front there is my scalar. What do we get when we do scalar multiplication? What's the first entry in our matrix going to be? 15. Okay. And then this next entry would be -3. And the next entry would be 0. And then this one would be 6. And this one would be 9. And this one would be 3. How did we get those values? Just multiplied 3 by every entry in our matrix, right? Is there any restrictions about when I can or cannot do scalar multiplication? Nah. We can always do scalar multiplication. There's no issues there. Everybody okay with these two operations? These should have been pretty easy to handle, right? What I want to talk about today then is the next operation, which is matrix multiplication. And while these first two operations that we've talked about, addition, subtraction, and scalar multiplication, have been really intuitive. There's nothing kind of odd going on here. Matrix multiplication here is a little bit not probably what we'd expect. But it's not too difficult, but it's not at all what you'd expect. So I'm not going to make that a column, make it a constant. Okay, so the first things first, the product of two matrices is defined only when the number of columns in matrix A is equal to the number of rows in matrix B. So here, do the dimensions need to be the same? No, only part of the dimension needs to be the same in order to do the matrix multiplication. And in fact, two things with the same dimension might not even be able to be multiplied together using matrix multiplication. We'll do some example here in a moment after I finish the rest of the definition about when we can or cannot do matrix multiplication. But that's already decidedly very different than the operations we've looked at to this point. Furthermore, we can say that the dimension of the product, so we can tell already what the dimension of the answer is going to be, since these two matrices that we multiply together might not have the same dimension. What would the answer's dimension look like if they don't have the same dimension? Well, the dimension of our answer is going to be the number of rows from the first matrix by the number of columns from the second matrix. Again, we'll do some numeric examples here in a moment to kind of, cement this in and firm things up a little bit to be really specific about what we're saying here. So to find the entries in the product, we're going to multiply each entry from each row in matrix A by the corresponding entry in each column of matrix B, and then add up those little products, and that'll give us the new entries in matrix, or in the product. So let's look at some examples. So we're going to look at whether the multiplication is possible, and if it is, what will the dimension of the product be? So we'll just do a couple of examples here to kind of get used to figuring out if and when matrix multiplication is possible, and then what our answer is going to look like. So let's say I take a 2 by 3 matrix and multiply it by a 3 by 5 matrix. Is that possible? Well, the rows in matrix A are the same as the columns in matrix B. So yes, we can do that multiplication. So my answer, I'm going to call it matrix C. What will the dimension of our answer be? It'll be 2 by 5. What if I say I want to multiply a 2 by 3 matrix by another 2 by 3 matrix? Is that possible? You cannot do that matrix multiplication. Why not? Because the columns of matrix A and the rows of matrix B are not equal. They're not the same. What about this? Is this possible? A 2 by 2 multiplied by another 2 by 2. Yes. All right. What would the dimension of the answer be? Also 2 by 2. Okay. So we see that sometimes if the dimension is the same, you can multiply them together. Sometimes when the dimension is different, or sometimes when the dimension is the same, you can't, right? Similarly, if the dimension is different, sometimes you can multiply them together if the dimensions are different. Sometimes you can't. Sam? That's not a 2 by 2 by a 2 by 3. That's a 2 by 3 times another 2 by 3. Because the number of columns in matrix A are not the same as the number of rows in matrix B, right? And you'll see when we do the numeric example why that needs to be the case. Okay, we'll do some in just a second. Everybody feel okay about figuring out when you can multiply two things together and when you can't? It's not too hard to check, right? The way that I like to remember it, the way I describe it, or the metaphor that I would use to describe it, is that multiplying matrices is kind of like falling in love. You can have two people, and they may look different on the outside, but really they're the same on the inside, right? And when two people fall in love, they have a child, and the child is going to look a little like one parent and a little like the other parent. Yeah, that's what I'm going to do next. But that's how you remember when you can multiply two matrices together. Just remember, it's just like falling in love. All right, so let's look at a numeric example here. So I'm going to color code this just to, I think it helps initially. But eventually I'm going to stop color coding these things, just FYI. Okay. So the first thing that I'm going to do is I'm going to check the dimensions to make sure I can do this multiplication problem. What's the dimension for my red matrix here? That's a 2 by 2. And what's the dimension for my green matrix here? 2 by 3. So is it possible to do the multiplication here? Yes. And what would the dimension of my answer be? 2 by 3. So what I'm going to do is I'm going to start by making a spot for my answer. And I'm going to put in a blank for each of the 6 entries that are going to go in that 2 by 3 matrix. Okay. So remember when we name the entries in our matrix, this would be like entry 1, 1 because it's in the first row and first column. This guy would be like 1, 2, 1, 3, 2, 1, 2, 2, and 2, 3, right? Is how we name those entries. In addition to helping us name the entries, this is also going to be helpful for us for matrix multiplication purposes, because the location of the entry is telling us which row and which column we multiply together to get that specific entry. So the entry 1, 1 is telling us I used row 1 and column 1. So when I do that, I get 2 times negative 1, and then negative 3. I wanted to write that in green. Times positive 2. And then I added those, and I'm going to add those two together. So I took the first entry from the first row and multiplied it to the first entry in the first column. And then I took the second entry in the first row and multiplied it to the second entry in the first column. And then when I add those things together, that's going to give me the first entry in my product. Okay. Now I'm going to go and I'm going to do this entry 1, 2. So again, I'm using the first row, but now I'm using the second column. So I'm going to do 2 times 0, and then negative 3 times 3, and I'm going to add those two together. I'm going to move to my next entry. This is entry 1, 3, so I'm still using the first row, but now I'm using the third column. So I'll do 2 times 5, and then negative 3 times negative 4, and then I'll add those. Now I'm going to move to entry 2-1. So now I'm using the second row and the first column. So I'm going to have 4 times negative 1, and then 5 times 2. And add those together. Next is entry 2-2. So that's the second row and the second column. So I'm going to have 4 times 0 and 5 times 3. And I'm going to add those two together. And then the last entry is entry 2-3, so second row, third column. So I'm going to have 4 times 5, and then 5 times negative 4. And I'm going to add those together. So on your test or quiz, I would expect to see this as an intermediate step. This would be the only intermediate step that I would need to see, but I would need to see this to make sure that I know that you know how to do this matrix multiplication process. From here, we're just going to multiply out each one of these little multiplication problems and add them together to get our answer. So I'm going to get negative 2 plus negative 6. That's going to give me a negative 8. 0 plus negative 9. That's negative 9. 10 plus 12 is 22. Negative 4 plus 10, that's 6. 0 plus 15, that's 15. And 20 plus a negative 20, that's 0. So, the takeaway here, the process for matrix multiplication, surprising, right? That's not intuitive. That's not what we would have expected to have to do. The process itself, though, not terribly difficult, right? All you're doing is doing like single number multiplications and then additions. It's just about getting things in the right place that's a little bit tricky. But once you've got a feel for it, it's not so bad, especially considering if you know what your answer looks like, the locations of your answer tell you what two things you're multiplying together, what row and what column to use. So it's hopefully makes life a little bit easier in putting those things together. Let's do one. Yes? Sure. Let's do another example of this, just multiplying things numerically. Harley? Sure.
Please excuse this interruption in the high school. Any shadows who have gone with their siblings that are in class now, you could head to the media center at this time. We're ready to begin. So any shadows who might be in classrooms in the high school, you could head to the media center at this time.
Sean, you good? Okay. No problem. So let's say we want to multiply these two matrices together. What's the first thing we should do? We have to check the dimensions, right? What's the dimension for this first matrix? That's a 3 by 2. And what's the dimension for my second matrix? 2 by 3. Can we multiply these two matrices together? Yes, right? What is our answer going to look like? It's going to be a 3 by 3. So I'm going to draw out a space for my answer. I'll put in 3 spots to write my answers in each row, and then have 3 rows. And I'll label kind of which spot each of these is. Help me remember which row and which column I'm going to use to do that multiplications with. Is everybody so far so good? Okay. And I'll still color code this one. This will probably be the last one that I'm going to color code though, just FYI. Eventually we're going to have to do this without having to color code things, but I think initially it's really kind of helpful to see where things are coming from, right? You guys thought that was useful the first time through. It'll probably be useful in your notes again if you go back and look at the class notes or whatever. Even if you didn't color code yours, you can look at mine from the class page or whatever. Okay, so the first entry is row 1 with column 1. So that's going to be 2 times 2, and then -1 times -2. And then we'll add those together. And then we're going to have row 1 with column 2. So that's going to be 2 times 5 and -1 times 0. And then the next one is row 1 with column 3. So I'm going to have 2 times 0 and -1 times 1. And I'll add those together. And I'm going to pause here and let you guys try to fill in the rest of this here. So just in your notes or whatever, try to fill in the next 2 rows for this matrix, and we'll go through it again in a moment when we're done. Yes, go ahead. So you guys take a minute and try to fill in the next 2 rows on your own, and we'll go through and I'll fill them in here in a minute when we've given you guys a chance to try it. But it's important that you guys get a chance to try this before you actually have to do it. Gives me a chance to eat my snack too. Okay, are you going to return it? No. Okay, so I have mine filled in there. Is that what you guys got? Just to point out a couple of patterns, if you look at the red numbers in row 1, what do you notice? They're all the same. Red numbers in row 2, all the same. The red numbers in row 3, all the same. What about the columns? Notice the green numbers in the columns are all the same, right? The red numbers are all different, but the green numbers are all the same. That's kind of true throughout. That's a nice little check that you can look at your work and go, oh, darn it. I goofed that up because, look, those aren't all the, they're not all the same. Okay, so we still have to get our final answer out of this. So let's see, 4 plus 2, that's 6. 10 plus 0, that's 10. 0 minus 1 is negative 1. 0 minus 10 is negative 10. 0 plus 0 is 0. 0 plus 5 is 5. 2 minus 12 is negative 10. 5 plus 0 is 5. And 0 plus 6 is 6. So that's what my final answer would be. Everybody okay with this? Okay. It's time to start asking some properties questions about matrix multiplication. And we'll start with the first question. Is matrix multiplication commutative? What do you guys think? What do we mean by commutative? We mean A times B is equal to B times A. Should answer no. We've already demonstrated why this is not true in general. What would our counterexample look like? So I think we had an example similar to this before, right? Where we said, okay, I'll take a 2 by 3 and multiply it by a 3 by 5. If I do that, I get a 2 by 5. But if I change the order, what happens there? Can I do the 3 by 5 times the 2 by 3? No, this is undefined, right? So in general, matrix multiplication is not going to be commutative because the dimension isn't going to work out. Well, what if we change this question to be what if the multiplication is possible both ways, A times B and B times A, then is it commutative? What do we think there? If I'm going to limit or I'm going to restrict this situation down to a case where, yeah, if I do A times B and B times A, both of those are possible. Is it going to be commutative then? What's my counterexample going to look like? What if I do a 2 by 3 times a 3 by 2? What's that answer going to be? It's going to be a 2 by 2, right? If I switch the order, I'd have a 3 by 2 times a 2 by 3. What's that answer going to look like? 3 by 3. Can those two matrices be equal? Definitely not, right? Why can't they be equal? They have different dimensions, right? That's the first part of the definition for equal matrices. They have to have the same dimension. Well, duh. Okay. What if the multiplication is limited to square matrices? I.e., you have something like a 2 by 2 times another 2 by 2. The dimension part's going to work out, right? But there's another piece to having equal matrices, is that the entries all have to be the same. So I know if I multiply two square matrices, it's at least possible that these are going to commute because the matrices dimensions will be okay. Let's look at a specific numerical example and see if the entries are going to match up. Is everybody okay with that plan? Okay, let's multiply these together. The first one's my A and the second one's my B. When I do that, I get negative 2 plus 9 is 7, and then 4 plus 15 is 19, and then negative 1 plus 0 is negative 1, and then 2 plus 0 is 2. I did that just quickly in my head. You're not expected to be able to do that. So now we have B times A. So when I multiply the first pieces together, I get negative 2 plus 2, that's 0. And at this point I can stop, right? Why can I stop right now? Already the first entries are not the same. So what can we say about this situation? Still no. That's not enough. So the question that we're left with now is there ever a situation where matrices commute? Yes. There still is some situations where that A times B is going to equal B times A. But as what you've seen so far, it's going to be a very special situation. There's two situations that I would expect us to be able to come up with on our own thinking right now. So think about it for a second. Two matrices that you multiply them together, and you get the same answer whether you multiply them A times B or B times A. What's that? What's that? Okay, so you have two situations that are probably reasonable, where you have the same matrix for each of them, right? Obviously, if I have A times A, that's going to equal A times A, right? The second situation is if one of the two matrices is the zero matrix, then if you multiply them together, this is going to give you the zero matrix, and that would give you the zero matrix. So remember that the capital letter O there we've used to represent the zero matrix. That's a matrix with all zeros in it. Now, are these the only two situations? Those are the two that I would have hoped you guys could come up with. Are these the only two situations? Nope. There's two more important ones, but we're going to come back to those. My next question is going to be, I'll put a 3 and a 4 here to remind us to come back to those other two situations. My next question is going to be, what is the multiplicative identity for matrix multiplication? When we say multiplicative identity, we want a matrix so that when we multiply it by A, we get A back, and that multiplicative identity needs to work in both directions. What do we think that multiplicative identity might look like? Let's just take a rolled matrix A and see what we're going to get. What do you think that, just take a guess. What would you expect? What's your intuition tell you that multiplicative identity might look like? Well, one thing right away, it has to be another square matrix, right? We established that those were going to be the only ones that could possibly commute, although they don't commute enough in general. What do you think the entries in that matrix might look like? I don't expect you to get the right answer right away. Just give me something that's plausible. One for each of them. That's probably I think I've asked the same question for like 10 years, and that's the answer that everybody gives the first time through, which is absolutely the place that I would start, right? That seems reasonable. Okay. So let's take a look and see what happens. So if I multiply the first row to the first column, I get 2 times 1 plus -1 times 1. And that's already not going to work out, right? Because what are we getting there? 2 plus -1, which is not going to give me 2 again. So what should we change in that question mark matrix? Which value needs to change? This one or this one? The second one. What should we change it to? What was that? How about 0? That gets us 2 again, right? So now the first entries match. Cool. Now let's do the second row and the second column. So I have 2 times 1 plus negative 1 times 1. When I do that, I get 2 plus negative 1, which gives me a 1 here, not a negative 1. So which entry should we change? The first entry, what should it be? 0. So if I change this to be 0, that goes away, and I have just negative 1 here. Okay? Now we'll do row 2 times column 1. So I have 5 times 1 plus 3 times 0. That gives me 5. That's good. And then we'll do the row 2 times column 2. That gives me 5 times 0 plus 3 times 1. That gives me 3. And now it works, right? So I can say the multiplicative identity for 2 by 2 is this matrix 1, 0, 0, 1. Actually, I'm going to reformat this. Colon here. So we know what the multiplicative identity for a 2 by 2 is. We figured that out ourselves. What do you think the multiplicative identity for a 1 by 1 is? This is exactly as simple as you think it would be. It's just 1. What do we think the 3 by 3 is going to look like? What's the first entry do you think it's going to be? 1. And then the next entry, 0. And the entry after that, try 0. And the next row, what do you think the first entry is going to be? 0. The next entry, 1. The next entry, try 0. It's a 50-50 guess. The third row, what do you think the next entry is going to be? Or the first entry is going to be? And the next entry, and the last entry, 1. So what do you suppose, or do you guys see a pattern now if you look at these 3? Where are the 1s at? Down that main diagonal. Where are the 0s? Everywhere else. So what's the 4 by 4 going to look like? And the next row, and the next row, and the last row. Good. Everybody feel like we got that? All right. So the multiplicative identity we give a special name to. What letter do you think we're going to use to represent this? Going to use the capital letter I. Why do you suppose we picked that? It looks like a 1. Yeah. Just like before, for addition, we picked the matrix O, or the letter O, to represent the additive identity because it looked like a 0. Because when I do addition of real numbers, 0 is the additive identity. Here we're picking the letter I for matrix multiplication for its multiplicative identity because it looks like the number 1, because 1 is the multiplicative identity for real numbers. So if we go back to our list, I know that A times I is going to equal I times A. So that's a case where matrices commute, is if one of the matrices is the identity element. So the next question we're going to ask, and this will be the last one that we can talk about today, and we will not finish talking about this one even today, which is fine. We'll just pick up next time, is asking, what do these multiplicative inverses look like for matrix multiplication? When I say multiplicative inverses, I want a matrix that when I multiply it by A, I get that identity matrix back again. And it needs to work in both directions. It needs to be able to A times question mark or question mark times A. Doesn't matter. I get the identity any way I do it. So this is going to be the fourth matrix that we discussed that is going to commute. Here it's not so obvious, right? So say we have this will be, say, our matrix A. Need to multiply it by something to get this. Actually, I want to change that. Pardon me. Let me do that. Do you suppose it's even possible for this to work? Not all the time, which is going to be weird, right? Not all the time is this even going to be possible to find such a matrix question mark. This one, there is one. That matrix will work. Let's just check real quick. So, first row times first column. Oh, shoot. That can't be negative there. So that one should be. Okay, now I'm ready. So 6 plus negative 5 is 1. My apologies, guys. And then the next row times next column. That's negative 15 plus positive 15. That's going to give me 0. Row times column. Positive 2 plus negative 2. That gives me 0. And then next row, next column, that's going to give me negative 5 plus 6, which is 1. So we see that this does work. It's possible, at least sometimes, that there is such an identity element. I'm sorry, such an inverse, or multiplicative inverse, right? Is the word I'm searching for there. So it is possible. These things do exist. I've shown you one of them right there. How do we find those, though, is a different question. And to answer that, we're going to have to define a new matrix operation. And this matrix operation is called the determinant. You may. The determinant is defined only on square matrices. And we're not going to give you a verbal description of how we calculate the determinant because it's really pretty terrible. And we're not going to give you like the general way to calculate a determinant because it's way beyond the scope of this class. What I am going to expect you to be able to do is calculate the determinants for 2x2s and 3x3s, and we'll show you kind of a visual way to do that. So for a 2x2, actually I'm going to do this abstractly. For a 2x2, we're going to take this diagonal, multiply it together, and subtract it from that diagonal, multiplied together. That's it. So that's not bad, right? Just basically make a little x. Guess what happens for a 3x3? Things get much, much worse. So to do this for a 3x3, the way we're going to do this, I'm going to show you what's called the diagonals method. To do this, we're going to start by recopying the first two columns of my matrix. And then I'm going to multiply these diagonals and add them together. And then I'm going to subtract from that these three diagonals multiplied together. So, we're not going to memorize the formula for a 3x3 determinant, because if you look at this thing, that's like an alphabet soup of confusion, right? There's no way I would ever be able to remember those letters together. No way, no how. But I can remember the process on how I got that, because it's super visual and it's kind of like, oh, I just do those three down diagonals minus those three up diagonals or whatever. We're going to stop here. Next time we meet, we'll do some specific examples and return to this idea of multiplicative inverses.